page 618, and we're going to look at something called piecewise notation. And piecewise notation is what we use when the domain is broken up on a function and you have different definitions for different parts. And they give an example of, here's the price if you want to go to a wildlife park in BC. Depending on how many people in your group, they make the price cheaper. So if you only had 9 people in your group, everybody's paying $10. But if you have a bigger group, school group from 10 to 99 people, they'll reduce the price to $8. And if you have a huge group, 100 people, everybody in grade 10 is going, then it's only $7. So we write that piecewise notation like this. We have some function, we put this big squiggle bracket, and then we list each piece separately with its specific domain. So the 10 part is only if n was between 1 and 9. The 8 part is when n was between 10 and 99. And the 7 part when n was bigger than 100. The most common place that we have a piecewise function is with absolute value functions. Because if I would draw the absolute value of x, and I'll draw it right here, I'll draw it in blue. The blue graph here is the absolute value of x. It has 2 different lines. It's putting this green line and this red line together. The green line is just x. The red line is negative x. And so instead of writing the absolute value of x, we could break it up into 2 pieces and say we have the green part when x is bigger than or equal to 0, and we have the red part when x is less than 0. And you'll notice the inequality, one has the equal sign and one doesn't. That's sort of a rule for function. You can't have the function defined in both pieces at the same time. So you get to choose. You get to choose, do you want to include the 0 with the first piece, or do you want to include the 0 with the second piece? So let's go to our example, and we're going to take each of these equations and write them in piecewise notation. It's going to be very important to find that critical point, that x-intercept, in order to do it. So you might want to start with a graph. And if I started with a graph, 2x minus 1, minus 1 would be my y-intercept of the inside, slope of 2, right? This dotted line here, this is 2x minus 1. So my absolute value, this part would stay the same. This part would get flipped up. And very important that at 1/2, I have my x-intercept. If that's the case, then my piecewise graph will look like this. Notice my green graph was identical to my dotted line blue graph. So part of your piecewise function will just be 2x minus 1. When does that happen? It was exactly the same when x was bigger than or equal to 1/2, because that was my critical point, my x-intercept. Right? This part of my blue graph was identical. This part got flipped up. What happens when you flip it up? All you're doing is taking your y values that were negative and making your y values positive. You make a negative y value positive by multiplying by a negative 1. So what we do in piecewise notation is we say, I'm going to take the original graph, which was 2x minus 1, and I'm going to put a negative out in front, because that negative will flip it up. Which I can write if x is less than 1/2, because it was when the graph was less than 1/2 that you'd have to flip that section up. And this part of the line that got flipped up is negative 2x minus 1, and you could distribute that negative. Does it make sense that this part of the green line is a negative slope but has a y-intercept at plus 1? So you could also just figure out that piece by thinking about y equals mx plus b that way as well. But it's nice to see that I could just take that original graph and flip it up. So you could leave it in brackets with a negative out in front. We can do the same thing with a parabola. So in B, I'm going to look at this parabola. In blue, I'm going to graph negative x squared minus 3x. And I notice it's not in vertex form. Okay, so what am I going to do? I could put it in vertex form. I could also put it in factored form. Factor out a negative x. The nice thing about the factored form is I would know that I have an x-intercept at 0 and an x-intercept at negative 3. I also know that my parabola opens down. Technically, my axis of symmetry, remember when we drew axes of symmetries with the red line? It would be halfway between 0 and negative 3, it would be at negative 3.5. Somewhere on this axis of symmetry, I'm just guessing right now, is going to be my x-intercept. Oh, how much? Yeah, I don't know exactly where it's going to be. But I know that my parabola would open down. Now, if I want to graph in green the absolute value of this, does it make sense that this section in the middle would stay the same? And this section would get flipped up, and this section would get flipped up. So now that I've thought about it graphically, it can help me write the equation. I know that the textbook wrote this in just 2 pieces. I'm going to actually write it in 3 pieces. I think it'll help you visualize it better. I'm going to start from my left and go to the right. So the first section is everything less than negative 3. Do you see that everything less than negative 3 got flipped up? So I could take my original graph, which was negative x squared minus 3x, and put a negative in front to show that I flipped it up. And that was when x was less than or equal to negative 3. My middle section between negative 3 and 0 stayed the same. So in that middle section, I could just write my original equation. That's from negative 3 to 0. And finally, the section that was bigger than 0, that got flipped up again. So I take my original equation, put it in brackets, put a negative out in front. That's when x was bigger than or equal to 0. So you'll notice in the answer key at the bottom, the textbook put the 2 parts that got flipped up, they combined them together and just wrote the domain as this one or this one. Which is perfectly fine. Also notice they chose different places to put the equal sign. You just need to include the equal sign somewhere. The only time that the equal sign will become really, really important is sometimes you can make a graph that the pieces are disconnected. Like, I could take a parabola and a line, and take a part of the parabola and a part of the line, and they actually jump in between. And then it would be important where you put the equal sign, because it would be like, is the point where it jumps, is it included on the line, or is it included on the parabola? But ours are all connected, and you can circle the questions 8, 9, and 13.